SenseNova-U1 Unifying Multimodal Understanding and Generation with NEO-unify Architecture, published March 5, 2026.
Oh, this is a big one.
It really is. So if you are an ML engineer or, an AI researcher tuning into AI paper podcast today, here is your 60-second summary for the short form edit. Imagine taking the absolute most advanced vision language models in the world right now and completely ripping out the fundamental components that allow them to, quote unquote, see.
Right, just totally stripping them down.
Exactly. No pre-trained vision encoders. Zero variational autoencoders. SenseNova-U1 basically strips away those lossy translation layers that have completely dominated multimodal architecture up to this point.
Which is wild to think about.
Right. Instead, it's a natively unified paradigm that operates directly on raw pixels and text tokens. It uses a mixture of transformers architecture to couple autoregressive text generation with pixel space flow matching. And it does this at a 32x compression ratio.
Yeah, and the benchmark results are just top tier.
Dominance across the board. Understanding, reasoning, any-to-image generation, all without those intermediate lossy bottlenecks. So that is the TLDR. Now we are going to dive deep into the source material and unpack exactly how they achieve this.
Because the engineering choices here, they basically flip traditional multimodal scaling entirely on its head. It requires a fundamental reset in how we even think about deep learning architectures.
Seriously, we've been so deeply reliant on the standard playbook for visual data that we almost accept its flaws as laws of physics at this point.
We really do. To understand why stripping out those vision encoders and autoencoders is so radical, you have to look at the landscape you're working with right now. It's completely fractured.
Right. You've got understanding happening in one silo and generation happening in another.
Exactly. And that fractured landscape is the massive bottleneck holding the whole field back. Currently, understanding and generation are treated as two fundamentally divergent mathematical problems.
Like two completely different languages.
Yes. If your model needs to understand an image, it passes it through a vision encoder, usually something like CLIP. But if you turn around and ask that same model to generate an image from a text prompt, it routes it through a latent variational autoencoder.
A VAE, like what they use in Stable Diffusion.
Right, so you have two completely distinct neural pathways trying to process the exact same conceptual reality.
Mm-hmm.
And that separation imposes totally divergent learning objectives during training.
I mean, you end up bifurcating the feature spaces, right?
Totally. And recent attempts to bring them together usually involve taking visual signals and heavily compressing them into discrete text tokens. Doing that utterly ruins high-level semantics and visual fidelity.
Because you're forcing a continuous visual world into discrete word-like buckets. It reminds me of a dysfunctional global corporation where, like, the research department speaks English and manufacturing speaks French.
Yeah, it is a great analogy.
And to build a product, they rely on this massive team of lossy translators, our VEs and VAEs. Information inevitably gets lost. Every single time you pass a concept through one of those encoders, you lose nuance.
But instead of trying to hire slightly better translators, the SenseNova-U1 researchers asked a much more difficult question. Why not just force everyone to speak a single native universal language from day one?
Which is a beautiful idea. But going back to first principles, that sounds incredibly risky. I have to push back a little on the practicality here.
It is a massive gamble, yeah.
Right, because you're throwing away millions of dollars of compute that went into training those vision encoders. Asking a model to start completely from scratch on visual understanding, how is that not just an extraordinarily expensive mistake?
Well, it's a huge leap to abandon those priors, for sure. But the gamble pays off because you eliminate those heavy intermediate translation modules entirely.
So it actually ends up being more efficient.
Exactly. If the base architecture can model both discrete and continuous spaces natively, it learns its own optimal representation. You aren't forcing the raw data through an artificial bottleneck just because it's convenient for the engineers.
The network just learns how pixels and text tokens actually relate in their rawest forms. Okay, so let's get into the mechanics of that raw input.
Let's do it.
Because SenseNova-U1 isn't using a traditional VAE to compress an image into a latent space. So how does the model actually perceive and draw raw pixels efficiently? Feeding raw high-res pixels into a transformer usually blows up the attention mechanism.
Right, the sequence length becomes completely unmanageable. This is where they introduce the near-lossless visual interface. Instead of using massive parameter-heavy encoders, they built an incredibly lightweight two-layer convolutional encoding.
Just 2 layers, that's tiny.
Yeah, it's super streamlined. The strides on those convolutions are set to 16 and 2. What this does is map the image into a sequence of visual tokens, where each token corresponds to a 32 by 32 image patch.
Ah, so that is where the 32x compression ratio comes from. You are still compressing the image to make the sequence length manageable.
But it's spatial and native, not a lossy latent translation cooked up by a separate model. It keeps the spatial integrity completely intact.
And on the generation side?
The output mechanism is just as simple. A multi-layer perceptron head, an MLP, directly predicts the pixel patches. It completely bypasses the need for those deep diffusion heads and VAE decoders.
Okay, but if you're an ML engineer listening right now, your brain might be throwing some serious red flags regarding the math.
Oh, I know exactly what you're going to say.
Right, because if the model is predicting pixel patches across vastly different image resolutions, say a tiny thumbnail versus a massive poster, you run into a huge variance problem.
The signal-to-noise ratio goes totally out of whack.
Exactly. Doesn't a standard unit variance noise prior completely destroy the SNR for higher resolution images? I would think the flow matching ODE would basically lose track of the signal.
That is a critical hurdle. You cannot just plug standard diffusion mechanics into this native interface. When the resolution shifts drastically, the standard math behind the noise distribution just breaks down.
Because the token sequence length changes so dramatically, right?
Exactly.
Yeah.
The researchers solved this with a brilliant innovation they called the dynamic noise scale. They introduced a resolution adaptive noise scale, denoted mathematically as sigma R.
Okay, walk us through how that normalizes the variance. How do they keep the ODE stable?
This mechanism dynamically scales the base noise using the square root of the token count relative to a reference token count. So as the image gets larger,
the token count goes up and the noise scales proportionally based on that square root.
Yes, and the effect of that scaling is profound for training stability. Whether the model generates a tiny thumbnail or a massive high-res poster, the per-token noise energy remains consistent.
So the overall signal-to-noise ratio is anchored perfectly. The flow-matching ODE always has a stable, normalized target. That is an incredibly elegant fix to a complex calculus problem.
It really is. Furthermore, they explicitly feed this normalized noise scale alongside the time-step embedding directly into the denoiser as a conditioning signal.
Oh, so the model always knows exactly what resolution regime it's operating in. That would prevent it from hallucinating low-res artifacts into a high-res output.
Precisely. So we have the inputs and outputs streamlined, the interface is near-lossless, and the variance is normalized.
But we need to talk about the brain in the middle, because processing autoregressive text generation, which predicts one discrete token at a time, and flow matching for pixels simultaneously, those are fundamentally different optimization trajectory.
Right, you'd expect catastrophic interference. But this is where the core engine, built on the NEO-unify architecture, takes center stage. It uses a native mixture of transformers, or MUTI backbone.
And they released two specific variants to demonstrate this, right?
They did. The first is SenseNova-U1 8E MOT, which is a dense 8 billion parameter model. The second is the A3B MOT.
And the A3B indicates it's a 30 billion parameter model, but with sparse activation, meaning it only uses 3 billion active parameters per forward pass.
Exactly. That sparse activation is absolutely key for compute efficiency. But the MOTI backbone itself is crucial because it routes different modalities to specialized expert neural pathways.
While still maintaining a shared underlying representation space, which is the holy grail here.
Right, but the real magic trick that binds text and images together spatially is the native rope EE, the rotary position embedding.
Oh, let's pause on that, because position embeddings are tricky even in standard LLMs. You have one-dimensional text where one word follows the next and two-dimensional images.
Yeah, it's a dimensional nightmare usually.
How on earth do you feed both 1D time and 2D space into the same positional embedding vector without completely blowing up your parameter count?
It's so smart. You reallocate the existing dimensions from the language model's embedding space. The native rope E takes the pre-trained LLM head dimensions and splits them across 3 distinct axes.
Temporal, height, and width.
Yep. Temporal, height, and width. It applies independent frequency bases to each of those axes simultaneously within the same embedding vector.
Wait, literally the same vector?
Yes. Think about how a text token behaves. It evolves purely along the temporal axis. So for text tokens, the height and width axes are essentially set to 0.
Oh, wow. And an image token carries physical spatial indices, so it evolves along the height and width axis.
Exactly. By splitting the embedding this way, the architecture unifies temporal and spatial encoding with absolutely zero additional parameters added to the network.
It's essentially hijacking the latent dimensionality of a standard LLM and mapping a 3D coordinate system directly onto it. That is wild.
And because of this unified structural grounding, they discovered something incredibly unique about how the model responds to generative guidance.
What happened when they coupled the autoregressive cross-entropy for text with the pixel flow matching?
Well, when they applied explicit image context guidance during generation, they found that it primarily enforces textual alignment. The explicit guidance parameter for images actually performed best at a relatively low weight of 1.
Compared to a text guidance weight of 4, right? So the text guidance just steers the semantics, but it doesn't override the visual conditioning the model naturally learned.
Right. The model inherently understands how to render the visual reality based on its native training. The text just points it in the right semantic direction.
It doesn't have to fight the text to draw a straight line or render a coherent object. But as beautiful as this theory is, I have to bring up a massive practical concern.
Let me guess. Serving this thing in production.
Yes. It sounds like an absolute nightmare. With a standard LLM, you rely on autoregressive KV caching to stream text quickly. But with image generation, you need iterative pixel space denoising, which sweeps over the full tensor multiple times.
It's a completely different memory access pattern.
Right. If you try to do both in one monolithic runtime, aren't you going to completely bottleneck the GPU?
You've hit on, arguably, the biggest hurdle for natively unified models. Serving them efficiently is notoriously difficult. But the paper explicitly addresses this system-level challenge with a disaggregated inference architecture.
Disaggregated meaning they split them up.
Yeah, they actually split the serving process into two entirely separate execution engines. An engine called LightTLLM handles the text streaming and control flow, while a dedicated engine called LightTX2V handles the iterative image generation.
So if text is streaming and images are iterative, one handles language and the other handles vision. It's like having separate prep and grill stations in a restaurant kitchen.
Or like a high-frequency trading floor where one algorithm is aggressively buying and another is aggressively selling.
But how do they communicate without slowing each other down? They must be passing their state ledgers back and forth constantly.
They pass those states through a dedicated bridge called pin shared memory. The two execution engines exchange generation states through this lightning-fast shared memory block without ever pausing to sync up through the CPU.
Which enables truly asynchronous scheduling.
Right.
So if a user sends a simple text-only request, it doesn't get stuck in a queue behind someone rendering a massive 4K image.
Exactly. In a live production environment, you can allocate entirely different GPU clusters to LightTLLM and LightTX2V based on demand. They operate independently but seamlessly swap states via that shared memory window.
That is a total game changer. But even with a dedicated GPU cluster, iterative pixel denoising is computationally expensive. The paper mentions integrating DMD2, right?
Yes, distribution matching distillation. DMD2 is critical for low latency serving. Flow matching usually requires taking hundreds of tiny mathematical steps. Those are your number of function evaluations, or NFEs.
And DMD2 lets you skip a bunch of those steps.
Basically, yeah. They taught the model to skip the microsteps and jump directly to the final visual distribution. The paper notes they crushed the NFE for image synthesis from 100 all the way down to just 8.
Slashing the math required by over 90%. That is insane.
It makes the pixel space denoising incredibly fast without sacrificing the fidelity of the native interface.
Okay, so the theory and infrastructure optimizations are impressive. But the real question is how this fully native encoder-free approach actually performs against the highly specialized models we rely on today.
The benchmarks are staggering, honestly. SenseNova-U1 rivals top-tier understanding-only models while simultaneously delivering incredible any-to-image synthesis. Take 1IG Bench, for example.
Which tests fine-grained generation across alignment, text rendering, and logical reasoning, right? In both English and Chinese.
Yes, so it isn't just overfitting to one linguistic structure. The 30 billion parameter A3B Métis model achieves leading alignment scores in English. And the AB Métis model absolutely dominates text generation within images in both languages.
So it's effectively solved the garbled text rendering problem that constantly plagues traditional diffusion models because it natively understands the character as a semantic token and the physical pixel simultaneously.
Exactly. And on Eigenbench, which evaluates the reliability of generated infographics, it significantly outperforms models like QuenImage and ZImage. On JEditBench for targeted image editing, it stands toe-to-toe with specialized editing models.
But what is truly remarkable to me is the capability for interleaved generation. The real-world utility here is just insane for you guys building applications.
Oh, absolutely. The use cases are endless.
We're talking about generating complex, text-rich infographics, rendering long-form text without bizarre misspellings, and creating entire comic books or slide presentations natively in one single pass.
And an unexpected byproduct of fusing these modalities natively is that they actually start feeding off each other during training.
The researchers prove that understanding and generation are actively synergistic, right?
Yes. Because of the native MOTI backbone, the deep text understanding anchors the image generation side. It allows the generative capabilities to converge rapidly during training with minimal objective conflict.
The model just leverages its deep semantic grounding to generate structurally perfect images. It's fascinating. So zooming out from the specific benchmarks, what does this unified architecture signal for the future of AI?
I think SenseNova-U1 definitively proves that the era of cascading pipelines and lossy VAE and VE translators is coming to an end.
Right. By operating directly on raw pixels and text tokens within a unified backbone, we achieve tighter semantic consistency and massive inference efficiency. But I want to leave you with one final provocative thought tied to the paper's conclusion.
The vision for the future they lay out is pretty wild.
It is. The researchers explicitly note that this native unified architecture points directly toward vision language action models and ultimately true world modeling.
It's the logical next frontier. If a model is natively processing the world as continuous visual streams and discrete concepts simultaneously, without translation layers.
What happens when you plug this architecture into a robotic body? Are we looking at the exact representation space required for true embodied AI to perceive, reason, and manipulate the physical world in real time?
Instead of a lossy translator, we might have just engineered the native language of physical reality.
Think about that the next time you look at a traditional diffusion pipeline. We will see you next time on AI Paper Podcasts.